Howdy, howdy, everybody. Root Beer here, taking a look at another math contest, specifically the 2003 Fermat paper, and we're actually up to the penultimate question, second last one, question number 24. And that's in part C, where each question is worth 8 marks. So let's give it a gander here. When the expression 1 plus x times 1 plus 2x cubed plus 1 plus times 1 plus 4x to the 9 times 1 plus 8x to the 27 times 1 plus 16x to the 81 times 1 plus 32x to the 243 times 1 plus 64x to the 729, all of that squared, is expanded and simplified. The coefficient of x to the 2003 is, and then we have some options, 0 and then a bunch of powers of 2. Okay? I'm not inclined to believe that it's 0, just because I think you would probably have to get a negative sign. I don't see a negative sign. That said, if it turns out to be 0 by some other means, there are other ways to get 0, but I think when we expand this, we're definitely going to get at least 1x to the 2003 somewhere in there. Okay, so what's jumping out at me as I read this? Well, I'm noticing a pattern to each of these little bracketed expressions. I feel like I'm going to need some more space, so I'll already flip the page here. So we had 1 plus x, and then we had 1 plus 2x cubed, and then we had 1 plus 4x to the 9, and then 1 plus 8x to the 27. And at this point, I would say the pattern is becoming kind of clear. In general, each of these terms is 1 plus 2 to the something, x to the power of 3 to the something. Okay? That's what each of these terms is looking like. And we go all the way up to, I think, 729. So that's 3 to the 6. Okay. So there's that pattern, and that's interesting. The first thing that hits my mind is binary and more specifically ternary. I say binary just because a lot of people, when I say ternary, it doesn't immediately sort of click in their heads. So binary, if you know anything about computers, and hopefully at this point you probably do. If you're taking a grade 11 contest, you probably have seen some grade 11 material. And so you should be aware, computers use zeros and ones for the most part to perform their calculation. And every number can be written in zeros and ones. 1 is 1, 2 is 1, 0, 3 is 1, 1, 4 is 1, 0, 0. These are binary expressions, ways of writing numbers out using only ones and zeros. Ordinarily, we write our numbers decimal, and that uses zeros, ones, twos, threes, fours, fives, six, sevens, eights, and nines. But there's no single digit that represents 10 or 11. Okay? There can be in other systems. Hexadecimal comes to mind. Ternary is just writing things in terms of powers of 3, and so you'll have only zeros, ones, and twos. Okay? And so that immediately springs to mind just because I see x to the 2003. So I think, how can we get that 2003? Well, we have to multiply a bunch of the other x to the various powers. And those x to the various powers are to powers of 3. And when I multiply x to the something times x to the a times x to the b, I get x to the a plus b. So now I'm thinking, how can I express 2003 as sums of different powers of 3? And that's exactly what ternary does. Just like binary expresses things as sums of different powers of 2. Okay? So that's what's just jumping into my head as I read this. Now, 2003 is a big, scary number, and this is a big, long, scary expansion. So what I'm actually going to do is I'm going to take a look at something simpler. And this is a nice way to do things. I'm going to instead ask, what is the coefficient of, x to the 13 in the expansion 1 plus x, 1 plus 2x cubed, 1 plus 4x to the 9, And I can't forget that everything got squared. Okay. So these are much smaller numbers. I could actually expand this whole thing out if I needed to. But with smaller numbers, I can get a better understanding of the situation. Then I can take what I've learned and apply it to the big number, 2003. Okay? So, well, the first thing I want to do is I'm going to distribute this power of 2. Okay, and once I have that, I can use the binomial theorem to really quickly expand these. 2x and an x squared. Then I have a 1. I'll have 2 times 2, so that'll be 4x cubed plus x to the 6. Oh, no, it should be 4x to the 6. And as I'm doing this, I should always be mindful, are there any other patterns I'm seeing that I could take to the big case? 1 plus, it'll be 2 times 4, which is 8, x to the 9, plus, and then I'll have 16 x to the 18. Okay. So as I'm seeing this, I'm noticing that 1 plus 2 to the n, x to the 3 to the n, squared is 1 plus, we'll get an extra 2 here. And then I get 2 to the 2n, x to the 2 times 3 to the n. Okay. Things to think about. So this one here is almost this is just we could replace it with x to the 0 times 3 to the n, and this is x times 1 times 3 to the n. Things to think about. Because I'm trying to connect it with what I think might be related to this problem, which is ternary representations. Now, so I have, I need some more space, so we'll just copy this down again. (8x to the 9) and then 16x to the 18. Okay. Now when we do this, to make an x to the 13, a something x to the 13, I'll need to take something from here, multiply it by one of the terms from here, and multiply it by one of the terms from here. The 18 is right out. If I use the 1, at best I can use the 6 here and the 2 here. So the 1 is out, because that would just give me an x to the 8. So I have to have 8x to the 9. And then once I've got that, I've got x to the 4 to make up. If I use x to the 6, no, that's not going to work. If I use the 1, that's not going to work either, because at best I could use this x squared again. So I've got to have 4x cubed here. Once I've got that chosen, I have x left to choose. It's got to be this guy right here, 2x. Okay, so there was really only one way to get this x to the 13 here. And it would have 8 times 4 times 2, 64 x to the 13. That's the only way this is going to work. It's the only way to get x to the 13. Now, incidentally, if I were to write 13 in ternary, so this is how we convert something to ternary. I ask, what's the biggest power of 3 that's less than 13? And you would correctly say 9. Okay, how many 9s can I fit in there? Below 13. I can only fit 1 9. Then what's left over? I've got 4 left over. What's the biggest power of 3 less than 4? Why, that's 3. How many 3s can fit in a 4? 1 3 can fit in there. Okay, what's left over? It's a 1. What's the biggest power of 3 less than 1? 1. And how many 1s go in there? 1. So to write 13 in ternary is 1 1 1. And wouldn't you know it, we used the 9, the 3, and the 1. Okay. Can I get another example here? How about 21 in ternary? What's the biggest power of 3 less than 21? 9. How many 9s go into 21? Why, there's 2 9s. And it gives a remainder of 3. What's the biggest power of 3 less than 3? 3. How many 3s go into it? 1 3. What's left over? 0. So 0 1s will go in here. So 2 1 0 is 21 in ternary. So if you haven't seen ternary before, that's sort of your crash course there. I would recommend you look up binary and how binary works, and then move on to ternary if this is a brand new concept for you. Okay. So what have we got here now? So I think we write the number in ternary. And there should only be one way to do this, because each of these gives us one of the ternary expressions. So this is either 0 1s, 1 1, or 2 1s. This is either 0 3s, 1 3, or 2 3s. 0 9s, 1 9, or 2 9s. So there should be only one way to pick from each of the brackets. One term from each of the brackets. And use the corresponding coefficients. So I'm going to use 21 as a test. Rather than trying to expand this out, I know 21 in ternary is 2 1 0. So that's 2 9s, and this represents 0 9s, 1 9s, 2 9s. So I'm going to use 16 times x to the 18. And then my ternary for 21 has 1 3. So there's 0 3s, 1 3s, and 2 3s. So this is the term that represents 1 3. And then we have 0 1s. So here's 0 1s, here's 1 1, and here's 2 1s. This is the term that represents 0 1s. So if I multiply those together, I should get 16 times 4, 64, x to the 21. And that should be the only way to get 21. Yeah, that all works out. So now let's take this and apply this to 2003. In ternary is, okay, so what's the biggest power of 3 less than 2003? Judging by the question, I would say it's 729. Okay, that's definitely less than 2003. And the next power of 2 is 3 to the 7. So the next power of 3 would be 2187. Yes, and that's bigger than 2003. So 729 is definitely the biggest power of 3 less than 2003. Okay. So 729. How many 729s can we fit in there? 2003 divided by 729 is 2 point something or other. So we can get 2 of those. And now what's left over? 2003 minus 729 minus another 729. We've got 545. What's the biggest power of 3 less than that? Why, it's 243. How many of those can we fit in there? I think it should just be 1. Oh, it's 2. It's 2. And what's left over should be 59. What's the biggest power of 3 that fits below there? We have to skip over 81. There are 0 81s in there. But there are 2 27s, because 54. And then we'll be left with a 5. And so there'll be 0 9s and 1 3. And then that leaves us with 2, and so there'll be 2 1s. So 2003 in ternary is 220202. Oh no, sorry, there should be a 1 in there. 0 1 2. Okay. So this is 2 plus 3 plus 2 times 27 plus 2 times 243 plus 2 times 729. That should be 2003. What are we going to do now? Okay, so we have this information. And what do our sort of brackets look like? What are the coefficients we're stealing? So this is for the 1s. Then we'll have for the 3s, we'll have for the 9s, the 27s, the 81s, the 243s, and the 729s. 1 plus 4x to the 3 plus 4x to the 6. And we had 1 plus 8x to the 9 plus 16x to the 18. We'll have x to the 54, x to the 27, and we'll have 1s all the way in front of everything. X to the 162, x to the 486, and x to the 1458. Okay. So this should be double 8, so that's 16. This should be double 16, double that, and double that. And then these should just be the power of 2 squared. So these will be powers of 4. So this one will be 64. This one will be 256. And now I don't remember my powers of 4 that high. 1024. And then this one will be 4 times that. So it should be 4096. Okay. So we have 1, 2, so that corresponds to this one, and then another 2, so that corresponds to this. A 0, so that's this one. 2, so that's this one. A 0, so that's this one. A 1, so that gives us a coefficient of 4, and finally 2. So we're just looking for coefficients. We've got x squared times 4x cubed times 1 times 64x to the 54 times 1 times 1024x to the 486 times 4096 times x to the 1458. If you wanted to at this point, you could also double check your ternary expansion. Make sure that the exponents of all those x's do add up. So 2 plus 3 plus 54. In fact, I'll even grab my calculator and do this right now. 2 plus 3 plus 54 plus 486 plus 1458. I do in fact get 2003. So that's just a little confirmation that I did my ternary expansion correct. Okay, so now what's left? Just multiply out these coefficients. 1 times 4 times 1 times 64 times 1 times 1024 times 4096. 1 times 4 times 1 times 64. Now I don't remember what they were. 1 times 4 times 1 times 64 times 1 times 1024. Times 4096. Now, if I recall correctly, the question asks, gives us the answers in powers of 2, so it might be a good idea to convert these back to powers of 2. I'm going to drop all the 1s, so we get 2 to the 2 times 2 to the 6 times 2 to the 10 times 2 to the 12, I think. Let's double check that on my calculator. Yes, 2 to the 12. And so if we write this as a single power of 2, we just add the exponents, which is something we're familiar with, because that's how we stumbled upon ternary. So that's 2 to the 8 plus 10 plus 12. 8 plus 12 is 20, and then plus 10 is 30, so we get 2 to the 30. And 2 to the 30 is C. So that'll be our answer right there. Not bad at all. And there's not a whole lot else to do with this question, but we developed a general technique. We could do this. We could keep going with these this sort of bracketing and go up to other things like 1 plus 128 x to the 2187, things like that. And we could do any coefficient for any x to the whatever. And I think that's pretty neat. So we recognized the pattern and we generalized it, not just to answer the specific question, but if this had been, say, a written contest, we could have then done any of them. We could have written down our solution and our way of doing things, and it would have worked out in general. Now, if you didn't see ternary number systems before, I encourage you to look that up, and binary as well. But I'm going to move on to our final question on this Fermat paper, question number 25. So try that one, and I'll see you for that question shortly.